perform this policy improvement algorithm, then I can use this policy improvement algorithm. So more description about that example of navigating agents safely through the obstacles will be given in lecture number 2nd in path planning channel, lecture number 2nd or 3rd in the path planning channel. So now we are having policy improvement algorithm. Now suppose you are having a particular example in which your agent can move in 4 possible directions, that is upward, downward, right and left, and probability of taking each possible action is 1/4. But now suppose you are having another policy in which the probability of moving rightwards is +1 in a state S. Only in this state the probability of moving rightward is 1, and in all other states the probability of actions is given by the same policy, that is 1/4. So the policy pi, so the policy pi dash is different from pi only in state S, and in all other states these both policies are same. That is, both these policies say that in each state you take the action with equal probability. But this policy is different from this policy only for this state S, and in all the state S it agrees with this policy. So therefore we want to check that whether it is good or not to take action A, that is moving rightward, state S is encountered. So if you want to check this, then you will calculate the action value function for taking action rightwards, that is action A, in your state S. And now you will compare the two things. The first is action value function for taking action A in state S and thereafter following policy pi, and second thing is that you will compare the state value function for state S under the policy pi. So basically we will calculate the action value function for this state, that is, which is given by taking action A, which is moving rightwards, and then we will make a transition to state S dash, and here the probability of making a transition is simply 1 because all these actions are deterministic actions, and once these actions are taken, agent will surely move either in this state or in this state or in this state or in this state. So we calculate the action value function for state S, and for action A, that is rightwards, we will calculate this thing, and then we will compare it with the value function for state S. That is, you will calculate the value function for this state S. You are having the value function, you are having the value of this state, and now you will calculate the action value function for state S, and action is rightward. You will calculate both these things, and if this action value function for taking action rightward in state S is greater than the state value function for state S, then we can construct another policy pi dash, and this policy will be better than your present existing policy. That is, this value function, that is the policy pi is, that is the policy pi is saying that in each state you take actions with equal probability, whereas this new policy pi dash is saying that okay, you take every action with equal probability except in state S. So for state S we are calculating the state value function, and if it is greater than this state value function for state S, then we say that this policy is at least better than the present existing policy, and action A is in this example is rightwards. That is, now we repeat this process for every possible state. That is, we are having for all the possible states we calculate the we calculate the action value function according to the new policy. Suppose this new policy now says that in state S double dash the action moving upwards is an optimal action. So we again calculate this action value function for moving upwards in state S, and again we compare with the state value function under the policy pi, and if again it is greater than this, then we say that the policy pi dash is indeed better than or at least or equal to the existing policy. So this fact can be generalized to every possible state, and each possible action A, you calculate the action value function for each possible action in state S, and you compare it with the state value function and the action that is giving you the maximum value, and which is also better than the state value function, optimal. So by repeating this process iteratively, we can reach to the optimal policy. So in policy improvement, we consider a new policy that is greedy with respect to the current policy. That is, policy for this particular state S, you choose an action A that will give you the maximum value of this expression, and then you will make a transition to new state S dash, and from that state S dash you will follow the policy pi. So if you want to calculate, if you want to compare any two policies in a particular state S, so in that state you will choose an action greedily that will maximize this expression. So basically, in the original policy you were having the equal probability of taking each action, whereas in this policy you are taking the action that will maximize your expected return. So basically you are following a new policy that is greedy with respect to the current policy. So following this formula will give us an improved policy, provided that the present policy is not an optimal. In that case, we'll get the same policy in return. That is, if you are calculating the action value function, that is, if you are performing policy improvement over your optimal policy, then you will get the optimal policy itself. So this is basically a policy improvement algorithm. You choose any arbitrary policy, say pi dash, and now in each state is instead of following the policy pi, which is giving the probability for each action A, you just take the action that maximizes the optimal value function. That will maximize this expression, and you replace the probability of taking all the possible actions by this deterministic action. So you follow this algorithm iteratively, that will give you an improved policy for each possible state. And this is nothing but our policy improvement algorithm. So this is the final conclusion. If you see this expression, so if you perform this action and now you replace the policy pi with policy pi dash, that is, once you calculate that whether this policy is better than the existing policy, and then you iteratively run this algorithm, then finally you will get an optimal policy, and this pi you can replace with V star, and this will become V star of S is maximum over A summation of all S dash P S S dash times gamma times R A S S dash plus gamma times V star S dash. If you iteratively run this algorithm, that is, at each possible state you choose an action that will maximize your expected return, and you follow this process continuously. That is, you recursively run this algorithm, and then finally you will get the optimal policy. So basically this pi will be replaced with a star, and then you will get the Bellman Optimality Equation. Therefore the policy improvement must give us a better policy, except when the original policy is an optimal policy. So now we will consider the policy iteration algorithm. And policy iteration algorithm is nothing but a combination of policy evaluation and policy improvement. So as I said, you calculate you start with any initial policy pi, then you calculate the state value function for each state under policy pi, and then you perform the policy improvement. That is, you replace all the probable actions with a deterministic action, that is, the action that will maximize your expected return. Then you will get a new policy pi 1. You again evaluate the state value function for each possible state for this policy pi 1, and then you again perform the policy improvement, and likewise on continuously repeating this process of evaluation and